the copyrights of the people who are making these videos. So lecture number 4 is going to be about the casting processes, or what we call it the metal casting, solidification process, whatever the thing is. So first we're going to have an overview of the casting technology. We're going to talk about the heating process and the pouring process. Now that's different. Now you saw in the video we had the first one, we talked about a slightly higher than the melting temperature of the metal. Because if I get to melt the metal, it's not going to be viscous enough to be poured. And it's going to solidify before it's going to fill the cavities. So we have to talk about something called the pouring temperature. And then we're going to discuss the solidification and the cooling process after we fill the cavity. And we're going to cover the metal casting processes, the basic one, the sand casting. We saw an example for that. Other expandable mold casting processes related to the sand casting. The permanent mold casting processes like the die casting, where the mold is going to be used multiple of times. You saw in the example, he said that this can be used for 100,000 pieces. And we are going to talk about some foundry practice, the casting quality, and some product design considerations. So we start first with the solidification processes. Once again, it's just the process of the solid metal is going to be melted to be liquid, and we are going to pour it in the cavity. It's going to solidify that, and we're going to have the geometry of the part required. Solidification can be classified according to the engineering materials as the metal, but also I can do the solidification for the ceramic, especially the glasses. I can melt it and shape it. And also the polymers and the polymer matrix composites, which can be melted and solidified. So the solidification processes, once again, can be classified into casting of the metals, glass working, and the process of the polymers and the phase change materials. The casting, which is going to work on it, casting on the metal. Today we're going to cover the expandable mold, like the sand casting or the other related casting process, and the permanent mold casting, like the die casting process. Now, the casting is a very advanced process. Just think about if I'm going to make a part using the 3D printing, i.e. I'm going to put the layers after layers after layers to get the shape required. How much time do you think is going to take to make an engine block, small one for motorcycle, using the 3D printing? Days? And it's not going to have the same properties as if we're simply going to melt the metal, put it inside the mold, leave it to solidify. We're going to have the raw shape or the draft shape, machine it, and we're going to get the best quality for the shape and the material. So we can achieve complex part geometries. The most complicated shape can be made by the casting process if you're going to make a good mold for it. It can create both external and internal shapes. Any other machining, except the 3D printing, of course, you cannot work on the internal cavities. The casting is the only process which can work on the internal cavities. Just imagine the machining, the turning, the milling, the other things cannot work to make a channel inside the block. The casting can, especially sand casting. Some casting processes are going to be a net shape, other a near net shape. Net shape, that means the dimension we're going to get are going to be exactly like what I would like to have. And that's what we get in the die casting, because you saw in the example we saw in the video, he said that surface finishing is too good, because the surface finishing is going to be the replication of the wall of this mold. The mold has been machined to a high surface finishing, so the surface finishing I'm going to get for the part is going to be good. So I can take the part and use it directly. That's what we call the net shape. Others are going to be a near net shape. That's mean a minimum machining are going to be required to use the part after the casting process. The good example, the good practice is also we can have a very large parts are going to be possible. Just imagine an engine block for the ship. Something about the half size of this room can be casted. Some casting methods are suited for the massive production like the die casting. Just fill the mold and get the parts continuously. This is the bright side. We have the bad side. Now, first limitation of the mechanical properties. I'm going to melt the metal, I'm going to fill the mold, especially in the die casting. So the parts are not going to be too strong because it's going to fill the mold slowly. It's not going to be compacted. We can overcome this problem when I'm going to do the die casting because you saw that we pressurize the chamber. With cavity, the metal will be simply pressurized. But you remember that we said that we only can do it with the soft material. We cannot do die casting for the steel. Poor dimensional accuracy and surface finishing in some processes, especially sand casting. Dimensional accuracy because something we're going to talk about, we're going to melt the metal, the expansion will happen. I'm going to put it inside the mold cavity, start to shrink. So it's going to be slightly smaller than the actual size I would like to have, or maybe bigger. And also the surface finishing, especially in the sand casting, because the wall in the sand casting is not going to be as good as the die casting. We're going to have some porosity, and this porosity is going to be filled with some of the material which causes the bad surface finishing for the part. Because we're using the heat and we work with the hot molten metals, that's safety hazard. Also, environmental problem because we're using something to get burnt to melt the metal. So we can generate the footprint gases to the environment, and this will give the bad environmental problems. So it can do big parts, as we mentioned earlier, like the engine block, the heads for the automotive vehicles, wood burning stoves, the machinery frames, railway wheels, pipes, church bells, and extra. Small parts as small as the dental crowns, the jewelry, the small statues, and the frying pans. Now, overview on the technology. We said that if we would like to do the casting, we have to do it in a foundry. The foundry is the place where they're going to make the mold, melt the molten metal, pour it in the mold, solidify, clean it. So that's the place which is called the foundry. So obviously the person who's going to do that, the person who works in the foundry is called the foundry man. So the foundry man or the foundry men are the people who are working in the foundry. The mold in casting, okay, we should have a cavity, otherwise it's not going to be a mold. If it's going to be solid, well, I'm going to pour the metal in. So this cavity will remind the part shape. It's going to be the cavity, the air will be the same shape of the part I would like to cast. The actual size must be slightly enlarged. Now, why I should enlarge it? So I'm going to fill more metal. It's on the bigger size. When it's going to shrink, I'm going to get closer to the size required. So you have to remember that always the cavity must be slightly enlarged to allow the shrinkage of the metal during the solidification and the cooling process. Molds are made as vary of the materials, including we can use the sand, we can use the plaster, we can use the ceramic, and we can use the metal. For the plaster, sand, ceramic, they are the expandable type. We have to break it to take the parts off. For the metal one, it's going to be permanent. The expandable one can give you more complex geometries rather than the metal one. I can make complicated cavities with the sand casting because inside I'm going to have a sand. I can simply clean it and get the geometry required from the inside details. But for the metal, it's usually going to be a simple shape so I can open the die parts. We also can classify the molds into two types, the open or the closed mold. This is the oldest method. They actually were, in the old days, they were just doing a groove in the floor and put the metal in. And they start to simply forging it to make it hard. To get a complex shape, we have to do the closed type. This diagram, we are going to explain it later, and this is very important because it's usually a question in the final exam. You will see that we have 2 stars on this one. Two categories of the casting process, which are the permanent and the expandable. The expandable, as we mentioned once again, break up the mold. The permanent is going to be using it multiple times. The expandable is more complex shapes are possible to be made with. Disadvantage is the production rate often limited to the time to make the mold rather than casting itself. You saw the process. We use mechanical machine to do the compaction for the sand. Okay, this make the process faster, but if we're going to talk about the engine block, you cannot make it the same way. For the permanent mold, the mold is going to be made of metals and simply can be used to make many casting continuously. Advantage is higher production rate. Just close the mold, fill it with the metal, leave it to solidify. You can even increase the rate of the solidification by running a cooling channels within the mold to absorb the heat, increase the rate of the solidification, and increase the production rate. Solidification happen, open the mold, take the part off, close it, and redo it once again. But disadvantage is geometries are going to be limited by the need to open the mold. If I'm going to have complicated shape, the mold is not going to be open. The part will stuck inside. The other disadvantage is not mentioned here, is only can be used with the metal which have lower melting temperature than the mold material itself. If I'm going to use the steel, I cannot do a die casting for the steel. I can do the die casting for the aluminum, for the copper, for the brass, for the zinc, and so on. 2 stars here. Memorize all the details we have here. This is the sand casting mold. It's going to consist of 2 halves. The upper one is called the cup. The lower one is called the drag. So actually, previously in the exam, I remember when I was doing the marking, we have the same geometry, the same drawing without names, and you have to name these parts. Cup and drag. In between them, we have the partitioning line. Okay, the partitioning line. So this is the thing itself, all should be within the flask. We should have a pouring cup. Otherwise, it's going to be very hard to pour the metal in a small hole. So I do something like the flask, and this will be called the pouring cup. The pouring cup will take the metal to the downspur. Downspur will end up to the horizontal runner and start to fill the cavity. And if I would like to have the internal details within the part, I will put the core. Okay, so flask contains the mold. The mold consists of 2 parts, the cup and the drag. Partitioning line in the middle. This contains the cavity, the core if required. To send the metal to the cavity, I need a runner, which is going to be the horizontal. The vertical one is called the downspur, and it's going to need the flask at the top, which is the pouring cup. Now we have something called the razor here. Now this razor, when I'm going to fill the metal at the core, on the cavity, sorry. When it's going to be filled, I'm going to have some cavity here. So I'm going to put, some of the metal is going to be going up in the razor. It's going to have some pressure here. As the molten metal start to solidify and shrink, the molten metal here start to pressurize and push to fill the cavity generated around the shrink part. And thus I'm going to fill everything, and I'm going to overcome the problem of the small dimensioning for the part. Now, forming the mold cavity in the sand casting, I need something called the pattern. The pattern, for example, I would like to cast the shape of this bottle. So I have to make a pattern, usually is made of wood. And I have to cover it with the sand. When I'm going to do that, I'm going to have the same cavity of the part I would like to have. So the pattern is usually, the mold cavity is formed by the packing around the pattern, which has the same shape of the part I would like to have. When the pattern is going to be removed, the cavity of the packed sand has the desired shape of the part I would like to cast. Usually it's going to be oversized because we said we're going to have shrinkage. And the sand for the mold usually is going to be moist and contain the binder to maintain its shape. Otherwise, it will fall. So it always should be moist and we add some binder to it. So when you're going to compact it, it's going to be solid and reduce the cavity between the particles to obtain a better surface finishing. In the video we saw, they put something called the metal jacket to hold it further. Now, if I would like to have a cavity in the part I will cast, I need to have something called the core. So the core is provide the the mold cavity provide the external surface of the part, but the core is going to provide the internal cavities within the part. Usually, the core are going to be made of sand. Why sand? Why again to make it out of sand for the core? Just go back to the previous diagram. This is the core. Now it's a simple one, just cylindrical shape, but sometimes it's going to have some curves inside. So I make it out of sand because it's going to stay there inside the part when the solidification happens. If it's going to be made of any other material, it's impossible to get it out. But if you're going to have sand, I can use the pressure air, or I can use vibration, or both to remove the core and get the cavity inside the part. Of course, it's not just sand, it should be cooked sand. So it's going to be hard when you are going to hold it, but you can simply break it if you're going to add vibration to it. So these are an example for the patterns. This pattern made of wood to make the duction part in the engine block. Okay, so the pattern is usually oversized, so we're going to get the actual part. So that's how we can machine simply. This is a pattern for the pump case. They just simply machined on the router, and usually it should be varnished. Usually the varnish on the top, so it's not going to absorb the moisture. The gating system, if I only going to have the cavity inside the mold, without gating system, is useless. So the gating system is a channel through which molten metal is going to flow into the cavity from the outside of the mold. It consists of the vertical one, is called the downspur. The horizontal one is called the runner. And at the top, we need the flask, which is called the pouring cup, and this to minimize the splashing of the material outside the downspur. The riser, the part we saw in the just before the cavity, is a reservoir in the mold, which is the source of the liquid metal to compensate for the shrinking of the part during the part solidification. So when the part is going to shrink, we're going to have some cavity. The molten metal in the riser will start to fill these cavities and get the final shape. The riser always should be designed so it's going to be freeze just after the freezing of the original cavity of the mold. Now, once again, we said that the melting temperature by itself is not going to be enough. So we always need to increase the temperature to what we call the pouring temperature. So the heating and the furnaces are going to be used to heat the metal to the molten temperature sufficient for the casting. The heat required is going to be the sum of. First, we have to increase the temperature to the melting point. So we need the heat to increase the material to this temperature. And then we are going to add more heat or fusion to convert the solid to a liquid. Then we have to heat it to raise the molten metal to desired temperature for the pouring. Now you remember something called the viscosity. You studied viscosity before. Okay. Now if I'm going to talk about the honey, and the heated honey is going to be more soluble. So that's the viscous, which is represent the melting temperature. Going to increase the temperature further, the particle is going to be more viscous. So I can pour it much easier. It's not only for the pouring process itself, but if I'm going to have big channel inside the mold, I would like it to fill it before it's going to freeze. If I'm only going to melt it to the melting temperature, when I'm going to start to fill the cavity, it's going to solidify before it's going to fill the whole cavity of the mold. The pouring of the melting temperature is the first step to be successful. The metal must flow into all the region of the mold, and most importantly is the main cavity before it's going to solidify. The factor which is going to determine the success of the pouring of the melted metal are that we must reach the pouring temperature, and then the pouring rate, and the third one is going to be the turbulences. Now, if I get to reach less than the pouring temperature, once again, it's going to solidify in the way. If I get to have the pouring rate is going to be too slow, will cause the same problem. If I get to do it too fast, it's going to cause some turbulences. These turbulences will push back the metal to the bag. Also, the turbulences in the air trapped in will start to push the metal backward. So we have to care about these three main factors to get a successful pouring process. Most of the foundry men, actually, they can do that without even calculation because it's become part of their experience. Now, transformation of the molten metal back to the solid state. Usually that's what's happened. Now, what's happening here that this is the cavity, start to solidify first. You can see that the razor is going to start to solidify at the end because once again, it's designed to solidify later than the cavity itself. So what's happened in the case of the solidification of the pure metals? Now, I'm not going to cover that. Sorry, I'm not going to talk about that because you remember something about the liquidus, solidus, the other thing. You remember these words? If I'm going to have pure metal, how many melting temperature we're going to have there? Single. If I'm going to have for example, the brass, it's going to have the melting temperature of the brass, the copper, the steel. But if we're going to mix many things in one alloy, I'm going to have multiple melting temperature for each metal I have in this alloy. So once again, we said the solidification differs depending on whether the metal is going to be a pure element or an alloy. So you remember this diagram of the solidification and the melting temperature for the pure metal. So I'm going to pour the molten metal at the pouring temperature. It starts to liquid, the liquid starts to cooling rapidly until I'm going to reach the freezing point. And then I'm going to have the local solidification time until I'm going to have the freezing to be completed at the same temperature. Then it starts to cool down until I'm going to have the solid. It's going to be solid actually at this point, but it's going to cool down further until I can handle it. During this stage, from here, I'm going to have the shrinkage start to appear. So because of this process, what's happened is that when I'm going to start to pour the metal, whatever the temperature I have for the mold is going to be too cold compared to the molten temperature. Now, let's talk that the mold you have had 70 degree or even 100 degree temperature, but the molten metal is 1,500, for example. That means we have 1,400 delta T. So what's happening is we are going to have chilling at the wall. Chill is too cold compared to it. So you can see that this will be chilled very fast. The metal in the middle is going to slow down in the cooling. It's going to be less cooling rate than the outside one. So we're going to have something like the crust on the side, while the one in the middle is going to slow down, cooling down slowly until we're going to have the final solidification to appear. So we talked about that. Okay, so the skin thickness or the crust is going to increase gradually until we are going to have the constant temperature in the middle. Then the solid starts to solidify very slowly in the middle. So at the end, we are going to have around the on the crust, we are going to have randomly oriented grains of the small size near the wall. Because once again, because it's cooled down very fast, it's rapid cooling. That's why we have the small size, randomly oriented grains. In the middle, we are going to have larger column grains oriented toward the center of the casting, because once again, the solidification process in the middle are going to be as lower rate compared to the outside one. Now, this one is in red and underlined because once again, if you're going to have this diagram, you'll know what this describes. I'm not sure if this will be a question, but this is a possible question. Now, in the case of the alloy, in the alloy, multiple metals, at least two, thus we are going to have two melting points, two solidification points. So you remember that we said when one of them is going to be solidified, the other one remain liquid, we are going to have the states in between them, and we are going to call it liquidus. And when it's going to be solidified, it's going to be the case of the solidus. So if I'm going to pour the melted alloy at the pouring temperature, the liquid will start to cool. Then the freezing will begin at the higher temperature for the metal which have higher melting temperature. And this is stage, and the liquidus size, we're going to have one of them is going to be start to solidify, and the other one will solidify later. Until I'm going to have the freezing point completed, where both are going to be changed to a solid state. Then I start to cool down, and that's what we call the total solidification time is going to be from the freezing of the first metal till the freezing completed. So what's happened is going to be as following. Once again, the outside is going to be chilled very fast, start to cool down. The mixture in between them is going to be a longitudinal one, where the metal with the higher melting temperature start to solidify first. Then the metal with the lower melting temperature is going to be solidified seconds, and it's going to be solidified more rapidly because this one lost most of the temperature. So the characteristic range structure in the alloy casting showing that the segregation of the alloying components of the center of the casting will appear. If I'm going to cut the part, it's going to show up like that. This is a magnesium steel ingot after the removal of the slag skin from the surface. Solidification time simply can be calculated. Basically, what is going to be what will be the factor that will decide the solidification time? If you take a look to this part and the previous one, the solidification will start at the wall, then is going onward. That means the bigger part is going to take longer time for solidification. So the volume is the main factor. Solidification time, or the TS, is time required for the casting to solidify after the pouring process, and this depends mainly on the size and the shape of the casting by relation known as the Chevron's rule. So Chevron rule tells you that the time required for the solidification is equal to the Cm, which is constant, multiplied by the V, the volume, divided by the surface area, up to power n. Now, the V is for the size. Bigger size is going to solidify slower. But the geometry also going to play a role. For example, if I'm going to solidify 1 cubic meter of molten metal, if it's going to be 1 by 1 by 1 for the volume, it's going to be compact. And the surface area I'm going to have is going to be the exposed to the light to the air is going to be 5 square meter. That's the exposed to the air because the other one is going to be on the base. Okay. While if I'm going to do the same thing, but I'm going to make it as a flat plate, I will increase the surface area, so the cooling rate is going to be higher. So if this one is going to be increased, the time for the solidification is going to be decreased. If I'm going to make it a compact shape, reducing the area, but the volume remain the same, this will increase the time for the solidification. So the TS is total solidification time, V is the volume of the casting, A is the surface area of the casting, N an exponent which typically equal to 2, and the Cm is the mold constant. So the mold constant will depend simply on the mold material. It's going to be a permanent, it's going to be expandable, or it's going to be a sand, it's going to be a plaster, or it's going to be a gypsum. Also on the thermal property of the casting material. And finally, the pouring temperature relative to the melting point. Of course, there are constant value for all the CM depending on these three properties, and you can use it from the tables. The value of the CM is given in the casting operation are based on the experimental data. So they did the casting with different types of the mold material, different molten metal, and they found the CM. So you don't have to calculate your own. Just simply get the CM depending on the three factors, apply to the equation. You know how to calculate the volume, you know how to calculate the area, and this will give you what the time required for the solidification. Now, the main problem we have in the casting is going to be the solidification and the cooling process. Now, we will repeat the same thing. If I'm going to start to fill the molten metal inside the cavity of the mold, we said that we are going to have the crust generated on the surrounding. It's going to be chill. So delta T is too high, it's going to chill. The molten metal will remain in the middle. With this preliminary solidification process, the size will be shrinking. But this shrinking is going to be from the top. So you can see that the level will start to drop from the top. As the solidification will continue, the solidification will occur, the level will drop further. Again, to have the molten metal consists on the center where the heat rate diffusion is going to be less, and the contraction will force the part to leave the wall, shrink to the middle. And usually, if the pouring temperature and the pouring rate was bad, again, to have a cavity in the middle, and this should be removed. This is disadvantage. So, solidification shrinkage will occur nearly in all the metals because the solid phase has higher density than the liquid phase. The particle will simply be getting close to each other, so density will increase, so the part will shrink. The solidification will cause reduction in the volume per unit weight of the metal. The only exception we had is going to be for the cast iron, if it's going to contain a high carbon rate. Now, what's happening with the carbon, which is the graphite, is going to have the opposite thing. It's going to be expand when the temperature is getting lower. And thus, we're going to minimize the contraction in the part. But definitely, with the cast iron with the high content, it's going to be a brittle material, so it's not going to be applicable for many applications. The shrinkage allowance should be done, which is, as we mentioned earlier, the pattern should be oversized. So the shrink bond is going to be close to the desired dimensions. Okay, this oversizing is called the pattern shrinkage allowance. The casting dimensions are expressed by linearly, so the allowance should be applied accordingly. So, for example, increased by the width, the height, the volume, and the other things, and the same thing should be applied for the pattern. The directional solidification is another solution to overcome the shrinkage of the metal casting. So the previous diagram, in this one, we saw that everything will start to cool down from the surrounding. Again, to have some heat to be trapped in the middle. So what will be the best thing to make it a uniform solidification? I cannot send the air to the inside to cool it down, but I can simply provide an escape for the heat. So if I'm going to put, for example, a pin, which has a melting temperature higher than the melting temperature of the metal I'm doing. So this pin is going to work as an escape for the heat. It's going to absorb the heat from the middle and take it to the outside. And that's what we call the directional solidification process. So it's going to be either continuous feeding of the molten metal through the razor, will simply extend the present of the molten material in the mold cavity, and this will prevent the shrinkage voids. Or I can simply do by using these pins, which called uh, the chiller. Okay, I can put the internal chill, which is going to provide the escape for the heat from the middle to prevent the porosity we're going to have on the sides. For the external chills, another solution. Okay, I can put this one on the side within the mold cavity, which is going to encourage the rapid freezing of the molten metal in the thin section of the casting. And it's likely going to result, if the external chill are not going to be used, we're going to have the cavity on the side. The razor design, as we mentioned earlier, should be simply designed where it's going to contain the metal to be solidified after the actual part is going to be solidified. And thus is going to be a reservoir for the molten metal to compensate the shrinkage volume of the casting process. Now, for the casting processes, as we mentioned earlier, we have two major types, which are the expandable type and the permanent mold casting. So we start first with the expandable mold casting, and the most common example for that is the sand casting, where the mold is going to be made of sand, and we have to break it to take the parts off. So this is the definition. In the expandable mold casting, the mold needs to be destroyed to remove the casting, and the new mold required for each new casting process. The examples for the expandable casting are the sand casting, the shell casting, the investment casting. Actually, this is lost form casting. I'm going to change that now. Okay, lost form casting and the plaster mold and ceramic mold casting. In all these cases, we have to destroy the mold to take off the part. The advantages are more complex shapes are possible. That's the most advantage thing we can have. Besides, the sand casting can take the casting of any molten metal. Even it's going to have a melting temperature of 9,000 degrees, the sand is going to be the only process to do the casting for this metal. Disadvantage is the production rate, as we mentioned earlier, is going to be limited because we have to spend some time to make the mold. And contrary to the sand casting, in the permanent type, the mold is going to be used to make many parts because it's going to be made of metal. The example of it is the basic mold casting. We're going to have the mold made of metal. You don't have to press the metal in. We're only going to fill the cavity, solidify, open the mold, take the parts off. The die casting, the one which using the pressure. We're going to use the pressure to force the metal in. The most advantage of this one is the good surface finishing, plus it's not going to be shrink because it's always going to be under constant pressure. We always fill with the molten metal, so it's going to have the exact shape. Also, we have the centrifugal casting. If you ever wonder how they're making the big pipes, they make it by using the centrifugal casting. Spin it inside the die, so the metal will be simply built up on the walls, and then we're going to have the seam shape of the pipes. Advantage, higher production rate because we don't spend any time to make the parts. Disadvantage is less complicated geometries and limited to certain types of the metals. So we start once again with the sand casting as an expandable casting process, most widely used casting process, mainly because of the complicated shape we have. Nearly all the alloys, whatever the temperature is going to be, we can use the sand casting. It can cast metal with a high melting temperature, such as the steel, the nickel, and the titanium, because the mold specification which can stand a very high temperature. The casting range can be from the small parts to a very huge parts. Production quantities can be from 1 to million depending on the process of making the mold. If I get to have the mechanical method to compact the mold, I can make hundreds, thousands of parts every year, or even millions. This diagram is going to be very necessary when you are going to write down your report. The steps to make the sand casting. The first thing, we start from here. You have to make the core. If I need to have a cavity inside my part, I need to make the pattern. I start to prepare the sand, preparing the sand, make the mold using the pattern, put core if needed, prepare the raw material, do the melting, do the pouring in the mold I just made, waiting for solidification and the cooling, removal of the sand mold, cleaning and inspection, again to have the finished casting. Okay, so you will definitely using this one in the process of making the engine block. If you are going to use the sand casting. How to use the sand casting? How you are going to decide to use the sand casting? Because you know many of the new motorcycles are using the aluminum engine, right? So you have to ask your tutor when you're going to when they're going to explain the engine block for you. Does he want you to make exactly the same part, or he wants you to make any engine block which look like the original part with the dimensions and the properties? If he's going to start with the original part, you have to use the gray cast iron. The material for the engine block we have down there is called the gray cast iron. And the process for the gray cast iron casting is only going to be limited to the sand casting. If I'm going to use the aluminum to make the same shape, I can do the die casting. Aluminum, put in the die, and simply injecting the material to solidify. So these are the steps of making the sand casting. This is a very simple thing. I have the pattern, put in the box, making the top, the lower part first, the drag. So I'm going to fill it with the sand, compact it, turn it, take off the pattern. Go to the other side, do the same thing. I'm going to prepare the hole for the razor, for the runner, not the runner, sorry. The runner are the small cavities we are going to have in between the parts. Okay, now this one is the down spur. Down spur has been prepared. Cut extra material to make the pouring cup. Both halves are ready. Put one on the top of each other. Fill with the molten metal. Leave it to solidify. Take off the part. Cut off the extra parts. Clean it. We're going to get the duplicated shape. So that's how to pour the metal. We have this cavity for the razor. Otherwise, the air will trap in, and this will resist the filling of the cavity. Okay, so now these are the escape for the trapped air. So we're not going to have any cavity within the castle part. So a different shape has been done by the casting. Obviously, this one shows you the whole thing. So we had the core inside this one. We used the pattern to make the cavity. This is the razor. This is the pouring cup. This is down spur. This is the runner. Same thing here. This part should be trimmed. We have to take it off, recycle it, and do some finishing work on the casted part. So to make the patterns are used to form the mold cavity, and actually it's the full size model of the original part with oversizing. The pattern can be a single pattern. This can be two halves pattern. Instead of taking the pattern and make it for the two halves, I can simply separate it into two halves. Also, I can have it as two halves with the base. So I can make both, that similar to the one we saw in the video. So I can make both parts at the same time, then take the things, pull all the pattern, and start to do the work. And this is the cop and drag pattern. Each one. This one is even going to have details about the razor pattern, and it's going to have details for the runner. So the major requirement for the pattern and therefore the mold cavity is must be oversized to account for the shrinkage. The pattern materials can be made of wood, which is the cheapest material I can use. But the problem with it, that if I can, because you know that the sand I'm using is going to be moist, so it's going to be absorbed by the wood. So I can use the metal one. The metal is going to be heavier, but it's going to be used for a longer time. Also, I can use the plastic, which is going to be comprising between the wood and the metal, but I should choose a type of the plastic which can be machined to make the part required. For the core, okay, now this is the core. That's how it sits when it's going to be simply filled the metal. I'm going to have the cavity in the middle. So usually it's going to be fixed by the plastic pins, which are called the chaplets. The chaplet is going to be melt and disappear within the metal. So this is how to make the core. I'm going to have the core mold filled with the sand, with binding material, and I have to cook it. Just put it in the furnace so it's going to be solid enough to hold the high temperatures. So this is called the core boxes. I can make many of them, or I can make them as two halves, then stack them together to have complicated shapes. The foundry sand properties, usually we use the silica, which is the sand. But usually it should be mixed with the other minerals. Also, I should have some binary materials to hold the silica in between. The binding materials can be either organic or non-organics. One of the organic type is going to be the clay itself. So the silica have good refractory properties for the higher temperatures, small grain size for the better surface finishing of the parts. But the large size grains is going to be more permeable, and this allows for the gases to escape during the pouring process. I'm going to have bad surface finishing, but at least I'm not going to have a trapped air within the part. Irregular grains is going to be better because simply it's going to interlocking, and this will make the mold stronger. Disadvantage are the interlocking will reduce the permeability, so this will not allow for the gases to escape from the mold from the cavity. The binder used with the foundry sands are mainly going to be the clay. The clay will stack the silica particles or the sand particles to each other. Sometimes they're using some chemical materials to do the process, but this is the safest one because I don't want to contaminate the sand. This will be sent to the nature once again. So once again, that's what's happened if I'm going to have different size of the grains. If I'm going to have bigger size, I'm going to have bad surface finishing for the casted part. The smaller, better surface finishing, but this one have better permeability where the gases can escape through. The types of the sand molds we can have, the first one is called the green sand mold. Now green is not for the color, but the green that means is going to be moist. That's what we call the green. So mainly the green sand molds, mixture of the sandy clay and the water. Green means is moisture at the time of the pouring of the metal. Sometimes we use the dry sand mold. Okay, so instead of using the clay, I can use organic binder, chemical materials, and hold the parts. This will have need to be baked so to improve the strength. The scale dried mold, I don't have to dry everything because this will be time consuming. I only dry the skin from the outside, and this will make it something like a pottery thing, holding the part. Or simply, I can use the green sand mold, and put the metal jacket to hold the parts together. The mixing can be done in the foundry by using a very simple process. Put the sand at the entrance. Is going to be rolled in the roll number 1, then finalized at the wheel number 2, and we're going to have the sand exit to be used. The mold packing process can be done by hand, like the example we saw in the photos. I can do the machine packing if I going to need more forces to do that. And I can use the automated method for the massive production. Okay, now for the hand packing, I can make one mold every hour, for example. For the machine packing, I can do 3 or 4 times the amount of the hand packing. For the automated methods, I can make hundreds of molds every hour. The desirable mold properties are the strength, permeability to let the gases escape, thermal stability to resist the cracking if I'm going to put it at very high temperature, the collapsibility, and this linked to the first one with the strength, the ability to give away and allow for the casing to shrink without cracking the casing. Reusability, not the mold itself because I can destroy it, but reusability of the sand I'm going to use. Usually, if I'm going to use the organic binders, it's going to be limited to be reused once again. And that's why using the clay and the water as a binder is going to be much preferable than the using of the organic binders. Now, another method, they didn't want to use nor the clay nor the organic binders. And this was invented by the Japanese back in 1980s. So what's happening is they brought the sand, just the sand itself is going to be dry. They put it in the mold. It's going to have the over the pattern, okay? This is the pattern in the middle, filled with the sand. And then they're going to have the vacuum for the upper part and vacuum for the lower part. We're going to have the two halves, put them at the top of each other with the continuous vacuuming, fill the mold cavity, leave it to solidify. At the minute you're going to release the pressure, the mold will fall down. You don't have to break it. Now, what the advantage and what disadvantage of this one? The advantage is that the sand will be reused. We don't have any binder. It's just a sand. But the problem we have and disadvantage is the time to making the suction, negative pressure, to make it compact with each other, actually they're going to hold each other, is going to be time consuming, and this slowing down the process. So advanced sand casting method, the vacuum pressure effect is added to make the sand mold rather than the using of the chemical binders. And then the whole sand will be reusable because it's still clean. The advantage is easy to recovery of the sand since there's no binders. The sand does not require any mechanical reconditioning done when the binders are going to be used. And since no water is going to be mixed with the sand, the moisture-related defects are going to be avoided. But the disadvantage is slow process because the time of the negative pressuring is going to be too long. And till this moment is not adaptable for the mechanization. The other process is called the shell molding. So did anyone here try before to, for example, put his finger in the molten wax and try to take the shell off? Have you tried that before? Some naughty guys like me did that. So how many people here tried to do that? That's good. Okay. Now the same process is actually done in the manufacturing. What you're going to have, if you're going to put your finger in the molten wax, when you take off the shell, you will find your fingerprints has been printed there. So the same process can be done in manufacturing. I will get the pattern, put it in the soluble material, which can be sand with the resin, which is going to stuck on the surface. So when I'm going to take all that, I'm going to have a shell, have the same negative printing of the part I'm going to have. Make two halves, connect them together, support it with something, fill it, take it off, you will have the casted part. No sand, the pattern is going to use multiple times, good surface finishing. So the shell molding, also known as the DPM process, or simply can be called the ceramic shell molding process. The mold is going to be a thin shell of the ceramic or sand, and it's also called the shell mold. Since the solid naphthalene is going to be used for preparing the molds, the complicated shapes and the thin casting can be produced with this process. When we talk about the thin casting, is for example the fins for the heat exchangers. So this is my pattern. It's going to be heated. We put it over the dump box. The sand with the resin binders or the ceramic or the naphthalene is going to be here. Flip it, then flip it back. When I flip it back, a layer of the material is going to generate a shell over that. That's because of the high temperature. It's going to solidify very fast and create the shell. I repeat this process twice if I'm going to have the symmetrical shape. Okay, put it in the furnace to solidify it, take off the shell, put it in the flask, support it with the metal shots. That's only to prevent the collapse of the shell when I'm going to pour the metal. Pour the metal, solidify, I'm going to have the final shape. That's the shell molding process. Well, just give me an idea about apply that in the project in the advanced manufacturing. Okay, so these are the patterns. These are the shells. So you can see that we can generate the thin casting for the heat exchanging. That's repeating the same process as we mentioned once again. We're making the parts, we fill it with the molten metal to get the finished part. Massive production of that. Making many of these shells, pour the metal on all of them, leave it to cool down to get the required parts. The advantage is, and the main advantage is, a good surface finishing, up to 2.5 millimeters. Good dimensional accuracy with a plus minus 0.25 millimeters. Suitable for the massive production because you can manufacture these shells by mass. Disadvantage is the expensive of the metal pattern. The area of application in massive production of the steel casting were for the metal less than 10 kilograms in weight. The loose form is also an adaptable method we can use. Now this one is very simple. Again, to make the pattern made of foam. Now once again, I can make the foam mold filled with the material of the foam to have the geometry of the part required. Put this one in a sandbox filled with the sand. I'm not going to remove the pattern. It's going to stay there. When I'm going to pour the metal, simply is going to melt the foam and replace it. And by the end, I will get the cavity, which was actually filled by the foam, is going to be filled with the molten metal and get the shape required. It's called the loose form, also known as the loose patterning process or evaporative foam process or full mold process and the expandable polystyrene process. The pattern is going to be packed, foam pattern is going to make the mold cavity. This made, not mad. I have to change this one as well. Okay. Oops. Okay, so the pattern is made of foam, and as the molten metal is going to be poured, the foam will be evaporate and replaced by the molten metal will start to solidify. The polystyrene foam pattern is include the spur, the razor, the gating system, and the internal cores if needed. The mold does not have to be opened into a cup on drag section because simply it's going to be melt. We don't have to take it off. So these are some of the example. Engine block. The case for the pump. Okay, just make anything out of the naphthalene foam fill in the box with the sand, pour the metal through the downspur, and you get to have the part with very good surface finishing, as you can see. Mass production. So actually what he's doing here is just putting the things on the top of each other. So when he going to fill the big mold, he's going to make hundreds of parts at the same time. You only have to take it off from each other. The advantage is pattern need not to be removed from the mold, and this will increase the process of making of the mold. Simplifies and simply speed the mold making because the mold hulls are not going to be required as in the conventional green sand mold. Disadvantage is a new pattern needs to be done every casting because it's going to be evaporated. The economical justification of the process is highly dependent on the cost of producing the pattern. If this is going to be low cost, this will be a good advantage for the process. The application are the mass production of the casting for the automobile engines. Automated and integrated manufacturing systems are used to mold the polystyrene foam patterns and then feed them into downstream of the casting operation. Now, the investment casting using the lost wax process. Now, in this one, the pattern is going to be made of wax, but we're not going to evaporate it as we did with the lost foam because the wax needs to be reused multiple times. The main advantage for using the wax as a pattern is, you know that we have waxes melting at different temperatures, right? Have you ever seen the complicated shape for the valves when it's going to have different cavities inside? It has been done, all the cavities has been done by using the lost wax process. Multiple temperature waxes can make multiple layers, and each one is going to be melted at different temperature and leave the cavities inside. So the pattern is going to be made of wax, which is going to be melted after making the mold to produce a mold cavity. So this is an example, again, to make the wax pattern, put them on the wax spur, make something like the tree, just stuck them together. Then I'm going to put it in the slurry ceramic to make the shell. Okay, so I didn't use the permanent mold pattern to make the shell this time. I just used the wax one. Now I want to take this one off, heat it, melt the wax. You will have the shell, fill the shell with the molten metal. I got the parts. Now the area of application for that are small size but complex parts such as the art pieces, jewelry, dental fixtures from all types of the metal. It's used to produce the machine elements such as the gas turbine plates. Have you seen this one with the turning we had in it? This is the best way to make it. The pinion gears does not require little or no subsequent machining. So we can take the part, it's going to have very good surface finishing, and use it directly. So these are the making process for the pattern. Put it in the slurry material, solidify it, pour it, and you're going to have different shape. That's what we call the pattern tree. The advantage of the part is going to have a great complexity and intensity can be cast. Close dimensional control and good surface finishing. The works can be usually recovered and reused multiple times. And this is a net shape process. We don't have to do any additional machining on the part. Disadvantages are that going to be many processing steps are going to be required, a relatively expensive process. Now, sometimes instead of making the mold out of sand, we can use the plaster. Now, this one is the plaster like the gypsum, and we can copy any part to make the mold. It's going to be consist of multiple parts. Sometimes we can use it for multiple times, sometimes. So similar to the sand casting, except that the mold is going to be made of the plaster of Paris. In the mold making, the plaster is going to be plaster and water mixture is going to be poured over the plastic or the metal pattern, and allowed to get set. The wood pattern usually not going to be used because too much water in this case. It's going to stuck inside. The plaster mixture readily flows around the pattern as you can see here, and it's going to have fine details and good surface finishing for the wall. Advantage is good accuracy and good surface finishing, capability of making the thinner cross sections. Disadvantage usually need to be baked, otherwise the gypsum is too brittle. The mold strength, if lost over, is going to be over baked, is going to collapse for the gypsum. The plaster mold cannot stand high temperature because gypsum cannot stand high temperature like the other things like the ceramic. So simply, they thought about the ceramic. The ceramic mold casting, the same process as the previous one, but instead of using the plaster, we use the ceramic to do the mold. You know what's that, right? They call it the Japanese teapot. The heavy one is sold in the markets. So similar to the plaster mold casting, except that the mold is going to be made of the refractory ceramic material that can be withstand the higher temperature than the plaster itself. This can be used to cast alloys like steel, the iron, and the high temperature alloys. The application is similar to the plaster mold casting, except for the metal casting, which have higher temperatures. Advantage is good accuracy and surface finishing, also similar to the case of the gypsum part. So you can see simply we can add more details on the mold itself. It's ceramic, we can machine it to have the accurate details on it. Now the other type, all the 7 types we talked about earlier, we have to break the mold to take all the parts. The permanent mold casting, we can use it multiple times. The basic permanent mold processes are using the metal mold. All going to use the metal mold. The molds are going to be used for casting a lower melting point alloys. This is the problem we have. Okay. The mold itself is going to be made of the steel or the cast iron. That's why we cannot use it to cast the steel or the cast iron, because it's going to have the same temperature. They're going to be one part. Molds used for casting the steel must be made of the refractory materials, like what we had in the example of the ceramic type. So this is a simple mold casting process. This one doesn't have to pressurize the metal inside. So this one is also going to have the problem of the shrinkage. 2 halves, we have to clean it, add lubricant, close it using the pressure to force the things, but the point is going to be from the opening there. Fill it with the molten metal, leave it to solidify, take the part off. The main advantage for that is going to be the systematic process. Just pour, solidify, take it off. Clean it, close it, pour, solidify, take it off. The main advantage is the surface finishing, because this is a machine part, have very good surface finishing. So the surface finishing or the part generator is going to be very good. So advantage is good dimensional control and surface finishing. Rapid solidification caused by the metal mold result in a fine grained structure. So the casting is going to be stronger than the sand casting process. The limitation is generally limited to a metal with lower melting points, simple part geometries. Otherwise, I will not be able to open the mold to take out the part. The high cost of the mold is the main disadvantage, because it needs to be machined with very strong material. The die casting is another process. In this case, it's going to be more accurate parts can be used directly after the casting process. And that shaper process, the better surface finishing, better properties, no shrinkage will happen, simply because the metal is going to be injected under higher pressure. We just force it in and leave it to solidify. Exactly like the plastic molding process. Again, to have cavities filled with the plastic under higher pressure, solidify, then use the parts like the device I have in my hand. The process is going to be maintained during the solidification process. So we compress it and leave it under higher pressure. So no cavities are going to be happen and no shrinkage will occur. The mold is called the die, and that's why it's called the die casting. High pressure force the metal into the die, which distinguishes from the other permanent mold processes. So we pressurize it, force the metal to fill all the cavity under higher pressure. No shrinkage will occur. Solidification, take off the part and use it. Two types of the machines we had is either going to be the first one, which is die casting hot chamber machine. I can use the cold chamber machine. Difference between both is you can see that the melting temperature, the melting pot is going to be connected directly to the die. So I'm only going to pressurize it from here, fill the die with the metal, and leave it to solidify. Because it's attached, so it's always going to be hot, and this will be disadvantaged because of the grain creation. It's not going to be cooled down as the case of the other type, which is the cold chamber. In the cold chamber, I'm going to melt the metal separately. Then bring it with the ladle and add it to the piston, press it. So always the machine is going to be cold, and this will be an advantage. Even the die life is going to be longer. So advantage and limitations for the die casting. Economical for large production quantity. We can have multiple cavities in the same die. We can reduce the time for the solidification by running the water channel within the die. Give you good accuracy and good surface finishing. Thin sections are possible. Rapid cooling means the small grain size and good strength in the casting process. Disadvantage is usually going to be the limitation to the low metal points, and the part geometry must allow for the removal from the die, so we cannot use it for complicated shapes. The other type is called the squeeze casting. It's something like when you do it with the paste. So in this case, as you can see, all this part has been simply done by pouring the molten metal under the high pressure machine, negative and positive sides or male and female parts for the die, compress the metal, force it to take the shape of the pattern, so the cavity we have inside, and thus the part will be generated. Combination of the casting and the forging at the same time. The molten metal is going to be poured at the preheated lower die, and the upper dies will be closed to create the mold cavity as the solidification begins. Unlike the mold in the die casting, the mold have going to be closed after the introduction of the molten metals. Unlike in the die casting, you have to close it and then fill it. This one is going to be filled then closed to force the part to take the shape. Lesser pressure and finer surface details can be achieved compared to the conventional forging process. The semi-solid metal casting process with the metal alloys at a temperature between the liquidius and the solidus. It does have some solid parts and liquid parts at the same time. The alloy is going to be a mixture of the solid and the molten metals during the casting process, at what we call the Mishi state. To flow properly, the mixture must consist of the solid metal globules and the liquids, and this is achieved by simply stirring the mixture. So we are going to have the homogeneous liquidius process. The centrifugal casting, as we mentioned once again, is the process used to make the metal pipes, the big size one. And in this case, the mold is going to be cylindrical shape. Rotating on rollers. When you pour the metal, due to the centrifugal force, is going to be attached to the wall, building the layers, solidify, and we're going to have desired shape. Okay, I just mentioned that by talk. It can be classified into three groups. The first one is the true centrifugal casting. It's just what I mentioned. A pipe, you introduce the metal, The metal will be attached to the wall, something like the machine you have in the what they call it? I forgot. The spinner we have in what's the place near the Darling Harbour? Yeah, the spinning thing. Yeah, Luna Park in Luna Park. Yeah, what's the name of the machine? I forgot. Yeah, so send you to the wall. Same thing. The melted metal is going to be attached to the wall. We can have the semi-centrifugal casting, or we can have the centrifuge casting. Let's see what the difference between them. That's a true type. This is my mold. It's going to rotate on rollers, pouring the molten metal. It's going to be attached to the wall. Solidify layer after layer after layer until I'm going to reach the desired thickness. Leave it to solidify. I got the pipe. Okay, so I just mentioned that. Now I need to talk about this one. That's what will happen. Now, the characteristic of the centrifugal casting is continuous solidification will start from the outside surface due to the chilling effect with the molten metal eliminates the shrinkage and the inclusion from the casting. The centrifugal force will make the cylindrical shape with accurate consistency. Now, it always should be, in the case of the pure types of the centrifugal casting, it always should be a cylindrical shape. Otherwise, I'm going to have the offset in the rotation. No restriction, no stress-inducing factor during solidification, and make residual stresses are going to be minimum. So I don't need to do any heat treatment for the parts. Now for the semi-centrifugal casting, you remember the pulley we made by the sand casting process in the video. I can make the same part by spinning the mold. So I'm going to fill with the metal from the top. This will be a disc shape. So by centrifugal force is going to be attached to the outside. They start to build up from this end until it's going to reach the center. Now, the disadvantage of this one is the metal here is going to have the maximum centrifugal force. In the middle, what will be the spinning speed in the center? What will be the spinning speed in the center? Now, something like someone rotating around himself are going to the Luna Park in the machine and is going to have a big diameter. Which one is going to have more centrifugal force? Okay, now have you tried to spin the rope with the rock? The smaller one is going to be very low centrifugal force. When you extend the rope length, it's going to be higher centrifugal force. Centrifugal force in the middle, in the center of the rotation, is going to be equal to 0. That's why the part generated from this process is going to be too weak in the center. So usually we have to remove it. And that's what we have in the pulley. It should have a hole in the middle. So this centrifugal force is going to be used to produce a solid casting rather than the tubular parts like the pure type. Density of the metal in the final casting is going to be greater in the outer section. At the than the center of the rotation. The process used in the part which is center of the casting is going to be machined, such as the wheels and the pulleys. Now, the centrifuge casting, we're going to make a part, doesn't have any relationship with the mold we are going to have. It's the centrifugal forces is only going to be used to fill these cavities on the sides. Everything in the middle will be turned off, like this part. So it can be a cross shape, channels, and with the required shape of the part I would like to have. I can make them 8, I can make them 20, depending on the diameter I'm going to have. Pour the metal in the center, is going to be forced to go to the outside, and we're going to have a solid shape part generated. Some additional steps are required after the solidification process for all the processes we covered earlier. Now, you remember that we're always going to have runners. We have to trim these runners, we have to trim the razors, and so on. We have to remove the core if there's a core inside. We have to do some surface cleaning, especially in the case of the sand casting. We have to clean the surface. We have to inspect that. part? Is it going to be within the properties or offshore the properties? Is it within the dimension or not? Repair if required. For example, I did the casting, a part of the casting has not been filled. I don't have to scrap that. I can simply repair it by putting some molten metal on it, or simply I can put some, the welding process, just fill it with the welding material, then shape it. Something like filling the cavities in the teeth. And heat treatment to get rid of the residual stresses and make the homogeneous characteristic for the crystal shape. The casting quality is very important, and we have numerous of the opportunities for the things to go wrong in the casting operation. And these wrongs will result in a very poor quality for the product itself. This effect can be classified as the general defects, which is common in all the casting processes, but we have defects only going to appear in the sand casting process. The general defects are the misrun. If I'm not going to pour the metal at the exact pouring temperature, it's going to solidify before it's going to fill the whole cavity. We call this one a misrun. The cold shunt. Okay, this is the core. I'm going to have some small cracks on the top. So two portions of the metal are going to flow together. Now, because it's filled from here, filled from the other side, when they're going to meet, they're not going to meet at the molten temperature. They already start to solidify. So they're not going to be joined each other. And that's what we call the cold shunt. Actually, this is not X. What's happening is that this one is solidified here. The other one is solidified, so they are not mixed together. Now, once again, both these processes can be solved by increasing the pouring temperature before again to fill the cavity. The shrinkage cavity can be happen in all the cases except the die casting. Okay, so what's happened is that the depression in the surface, as you can see here, will cause the internal void to be caused by solidification shrinkage that contains an amount of the molten metal available in the last region to freeze. The cold shuts in this case is something like a small cavities. A metal spatters during the pouring, and the salt bubbles from the foam and become entrapped in the casting. The sand casting itself has its own problems, and the main problem is going to be because of the wall have some porosity. So the first problem we are going to have is going to be the sandy blow. If this porosity is not going to allow for the gases to escape, okay, we are going to have a cavity within the pot. The pinholes is going to be always going to be appear on the sides. It's a formation of many small gas cavities or slightly below the surface of the casting. The penetration, if I'm going to have big cavities in the wall, is going to be filled with the molten metal, and I'm going to have the penetration surface. This simply can be machined, and this is considered to be the easiest problem we have in the sand casting. The mold shift, if you didn't fix them good for the cup and the drag, is going to be shift when you are going to do the casting, and we're going to have the offset. You cannot fix this one. If it's going to be acquired sensible, you cannot fix it. Just destroy the things and do it once again. Now, for the furnaces we use for the melting of the metals, we can use the cobalts, direct fuel fired furnaces, crucible furnaces, electrical arc furnaces, and the induction type furnaces. That's it for the casting. We may have watched one of the videos before we're leaving. Oh, that's a good time. We didn't have a break, right? That's good. So you can go home earlier. So let's watch this video before we leave.